And I also need to share my screen. And let me get my whiteboard first. Okay, so now I have a whiteboard, so I can share my screen. Okay. So today we will look at special univariate distributions. Special univariate distributions. That's our main topic for today. So under this topic, we will look at a few distributions which are used frequently. There are many distributions. And when I say distributions, what I mean is we have either a PMF or a PDF which represents a particular distribution. So they are many, but we will just look at a few. And that's why our title is Special Univariate Distributions. Some of them are used more frequently than others. So we'll just look at a few. And I know when you look at a few texts, you'll find many more. But of course, we cannot go through all of them. So we shall just go through a few that are used frequently. And as we shall be looking at the distributions, we will look at them under two categories. In the first category, we shall consider discrete distributions, and in the second category, we shall consider continuous distributions. Remember, even when we introduced our random variables, we divided them into two. We considered the discrete random variables, then we considered the continuous random variables. So even for the distributions, we will consider the discrete distributions first, then we shall consider the continuous distributions. So just a small introduction to our special univariate distributions. So we can just write that probability models are classified into families of distributions distributions having common properties, with the PMF, or PDF, assuming a specified form, So I've just said that probability models are classified into families of distributions with the PMF or PDF assuming a specified form. Subtitle: Special Discrete Distributions. Special discrete distributions. So the first one we want to look at under special discrete distributions is the discrete uniform distribution. Discrete uniform distribution. Discrete uniform distribution. Definition: a random variable, capital X, a random variable, capital X, has a discrete uniform distribution, if it has PMF, f of x equal to f of x equal to 1 over n where x is equal to 1, 2, and so on up to n, and so on up to n, and it is 0 otherwise, So if we have such a PMF, then we know we are considering a discrete uniform distribution. And if you remember, it was applicable to the case of tossing a die. So for this distribution, how do we get the mean? For this discrete uniform distribution? We know that the mean is given by expectation of x, and because this is discrete, then we shall perform summation over the x values, f of x, summation of x, f of x. So this will give us f of x is a constant, which is 1 over n. F of x is a constant, and then summation of x is 1 plus 2 plus all the way up to n plus n. And remember how we handled 1 plus 2 plus many other values up to n, which was of the form of summation. Remember when we talked about summation of I, where I is from 1 up to n, and we made a substitution. So this will be equal to 1 over n. And when we sum over I using the SMP tables, it is the same as, or rather, the summation comes to n over 2 into n plus 1. So when we are considering the discrete uniform distribution, then we know that the mean is given by n plus 1 over 2, n plus 1 over 2, because n and n will cancel out. So the mean will be given by n plus 1 over 2. And if we want to get the variance of x, so we already know expectation of x. We need to get expectation of x squared so that we can calculate the variance. Expectation of x squared. So what's that? This will be summation. Summation x squared f of x, x squared f of x. And so if we substitute, what do we get? F of x is a constant, which is 1 over n. And summation of x squared implies that we shall be summing 1 squared plus 2 squared plus 3 squared all the way up to plus n squared. And so this simplifies to 1 over n, 1 over n into, as we saw the other day, it simplifies to 1 over n into n over 6 into n over 6 and n plus 1, n plus 1, and into 2n plus 1, 2n plus 1, and so it will be equal to n plus 1 into 2n plus 1 over 6. So now we can get var x. So the variance will be given by expectation of x squared is n plus 1 into 2n plus 1 into 2n plus 1 over 6 minus And expectation of x quantity squared is n plus 1 over 2 squared. So where am I getting this from? It is the one that we had calculated for expectation of x. So we know variance is expectation of x squared minus expectation of x quantity squared. So this term here is expectation of x squared. And if we simplify this, we get n squared minus 1, n squared minus 1 over 12. Over 12. If we simplify. Oh, there's a question. Okay, so somebody wants to know the name of the tables. These tables, and they are available at the bookstore. So the table is called, and I'm putting it in the chat, SMP. Yeah, it's called SMP Advanced Tables. You can get them from UN bookstore. I have put it in the chat. So you can look for that table from the bookstore. Okay, we continue. So why don't we look at an application, a question whereby we can apply what we have obtained about the mean of the discrete uniform distribution, and also what we have obtained for the variance of the discrete uniform distribution. So let's look at an example. Example, a discrete random variable x, a discrete random variable x has PMF f of x equal to 1/6 when x takes values x is equal to 1, 2, 3, 4, 5, and 6, and it is 0 otherwise, and it is 0 otherwise. So the question is, we need to compute expectation of x, compute expectation of x, and var x. We want to compute expectation of x and var x. So to get expectation of x, we already have the formula which gives us expectation of x, and it is n plus 1 over 2. So expectation of x is going to be, we just substitute where we have n, our n takes value 6. So expectation of x is just 6 plus 1 over 2 6 plus 1 over 2, and that is 7 over 2. 7 over 2. Maybe it's better to give the that we have. We can say that this is equation 1, and then the other one is equation 2. So to get expectation of x, then we substitute in equation 1, and that is why I wrote 6 plus 1 over 2. And so for that particular example, the expectation of x is equal to 7 over 2. The expectation of x is equal to 7 over 2. And var x will be equal to, we substitute in the second equation, and that will be 36 minus 1 over 12. And so var x will be 35 over 12. So we are saying that if we have a situation where the PMF belongs to the family of discrete uniform distributions, then we can easily get the expectation by using equation 1, and we can also get the variance by using equation 2. Equations 1 and 2 will help us to get the mean and variance. Let us go to the next distribution, which is also commonly used. The second distribution, known as Bernoulli distribution. Bernoulli distribution. So usually what happens with the Bernoulli distribution, it's a situation whereby you may have outcomes where you have only 2 outcomes, situations where you have only 2 outcomes. So we can write so we can say Bernoulli trials result in two mutually exclusive outcomes. Bernoulli trials result in 2 mutually exclusive outcomes. That is a success. Let me write that. That is a success. A success, small letter p. So the success is denoted by p, a success p, or a failure a failure, 1 minus P. Of course, P is a probability. So if the success is P, then the other outcome, which can be considered as a failure, is 1 minus P. For example, let's say that somebody does an exam, and then let us say that passing is a success. Passing is a success and failing is a failure. So passing is a success. So let's say the probability of passing is 7 out of 10. And passing is what we call a success. So if the probability of passing is 7 out of 10, then failing will have a probability of 3 over 10. So Bernoulli trials or situations whereby you have only 2 outcomes are usually modeled using the Bernoulli distribution. They are modeled using the Bernoulli distribution. Okay, so let's define the Bernoulli distribution. Definition of the Bernoulli distribution. Definition: a random variable, capital X, a random variable X has a Bernoulli, a random variable X has a Bernoulli distribution with parameter P, has a Bernoulli distribution with parameter P if its PMF is of the form, f of x is equal to p raised to x (1 minus p raised to 1 minus x p raised to 1 minus x. And because there are only 2 outcomes, then x takes values 0 or 1, either 0 or 1. Maybe for the experiment, and of course 0 otherwise. So why does x take only 2 values? We said that there are only 2 possible outcomes. So suppose that for a success, you assign the value 1. The success is the experimental outcome that you are interested in. So if you wanted to count, if you are interested in the proportion who pass an exam, then you can set 1 to be for those who pass the exam, and you can set 0 to be for those who fail the exam. There are only 2 outcomes. Okay, so now let us see how we get the mean for the Bernoulli distribution. Since discrete random, the expectation of x we know is summation of x, f of x. Let me just write that. Summation of x, f of x. And now you can see x takes 2 values, and f of x will depend on the value of x. So we are summing over x is 0 and 1. When x is 0, x f of x is just 0 because x takes value 0. When x takes value 1, then x is there taking value 1. And what is f of 1? F of 1 will be p raised to 1, multiplied by 1 minus p, 1 minus p raised to x raised to 1 minus x. 1 minus p raised to 1 minus 1, because we are saying that x is taking value 1. So what will that give us? It will give us p. So actually, we are saying that for the Bernoulli distribution, the expectation of x, which is the mean, is actually equal to the probability of success. It is equal to the probability of success, which is p. Okay, what about variance? For us to get variance, first we need to get expectation of x squared in order for us to get variance. So this is going to be summation x squared f of x x squared f of x. So again, there are only two values of x. When x is 0 and we substitute in x squared f of x, we get 0. And when x is 1, we have 1 squared multiplied by f of x. What is f of 1? F of 1, it will be p raised to 1 multiplied by 1 minus p raised to 1 minus 1. One minus 1, which is 0. So again, expectation of x squared is equal to p. I think this is why we are having online classes, so that if someone is coughing, okay, expectation of x squared is equal to p. Now, so what is var x? Var x, we know var x is expectation of x squared. Okay, let me write that first. Var x is equal to expectation of x squared, which we have found to be p, minus expectation of x. So I need to separate the p's. This one, okay, I just circled the two different p's. So expectation of x squared is given by the second p, and expectation of x is given by the first p. And so in calculating variance, this first p will be here and it should be squared, because we know var x is given by expectation of x squared minus expectation of x quantity squared. So this is equal to p into 1 minus p. P into 1 minus p. In some books, you will see that they write pq, where q is equal to 1 minus p. So we're just saying the same thing. In case you find yourself reading a number of books and you see that they write PQ, we are just talking the same language. Okay, why don't we look at an example where we can apply the Bernoulli distribution? There is a question. Okay. Yeah, somebody is telling us that somebody is asking whether this is similar to the MGF. Now, you know, yeah, last time we looked at MGF technique and we were able to get the mean and variance using MGF technique. And remember that for the MGF technique, we were saying that mx of t is equal to expectation of e raised to tx. And we were using the MGF technique to get the mean and the variance. Now, I am getting the mean and the variance again, that is true, but I'm not using MGF technique. I am using expectation to get the mean and the variance. So the difference is this. It is good for you to know how to handle the two different methods for getting the mean and the variance. Excuse me. I had, sorry, I had another lecture, so maybe that's why my voice is a bit hoarse, but at least I'm drinking something. I had a previous lecture. So I was saying that you need to know how to get the mean and variance using either MGF technique or expectation. So what I'm doing right now, we're not using MGF technique. We are using expectation to get the mean and the variance. Of course, whether you use MGF technique or you use expectation, you'll find that the mean will be the same for the same distribution. You'll find the mean and the variance are equal irrespective of the technique that you are using. But it is just good to know the two methods should you be asked to use a particular method. Okay, so let's go to the example on Bernoulli distribution. Example, a carton contains 4 good items. A carton contains 4 good items and 6 bad ones and 6 bad ones. A carton contains 4 good items and 6 bad ones. Define success as selection of a good item. Define success as selection of a good item. Then compute expectation of x and var x. Compute expectation of x and var x. So we need to know what our success is. We've been told that success is the selection of a good item. In that carton, there are 4 good items out of a total of 6. So, not a total of 6. 6 are bad. 6 are bad. So, the probability of a success is 4/10. 4 good ones out of 10 items. And of course, if that is the probability of success, then the probability of failure will be 6/10. So now we can get expectation of x. We can get expectation of x from equation 3. Let me call that 3. And this other one, let's call it 4. So from equation 3, we can see that expectation of X is given by P, the probability of success. Therefore, in this example of ours, expectation of X is equal to 4 over 10. It's equal to 4 over 10, which is the probability of success. And so what is the variance? Variance is given by equation 5. Variance is given by equation 5. So let us just substitute in equation 5 to get var x, then var x is the probability of success multiplied by the probability of failure. So 4 over 10 multiplied by 6 over 10. And this will give us 6 over 25. 6 over 25. So this is how we handle a situation which is modeled following the Bernoulli distribution. This is how we handle a Bernoulli distribution. So yeah, there is a question. You can write the answer in simplified form. You can simplify it more. That's fine. That's okay. Okay, let's continue. We want to look at the third distribution. Third distribution. The third one is the binomial distribution. Sorry. The binomial distribution. Binomial. The binomial distribution. So the binomial distribution comprises of small letter n, comprises of n repeated Bernoulli trials. It comprises of n repeated Bernoulli trials. And repeated Bernoulli trials. We are interested in the total number. We are interested in the total number of successes. We are interested in the total number of successes. Definition. A discrete random variable x. A discrete random variable x has a binomial distribution. Binomial distribution with parameters NP, has a binomial distribution with parameters n, p, if its PMF is f of x is equal to nx p raised to x if its PMF is f of x is equal to n combination x p raised to x 1 minus p raised to n minus x. And when does that happen? When x takes values from 0 up to n. Remember, or rather, and so on up to n. And of course, it is 0 otherwise or elsewhere. It is 0 otherwise or elsewhere. Now, x is the number of successes. Note that x is the number of successes. X is the number of successes. So we need to get again the mean and the variance. The mean and the variance. And so I need to share the slide containing that. Let me open it up. Then I share my screen. So first, we need to get the mean. First, we need to get the mean. And now, just as one of your colleagues asked, now we are getting the mean using moment generating function technique for the binomial distribution. So we know that our moment generating function, let me just expand it a little bit. Oops, that was too much. Okay, that's fine. But I will roll it down. Okay, mx of t, our moment generating function. We know the moment generating function is given by the expectation of e raised to tx. And so for this binomial distribution, our x values start from 0 up to small n. So because it is discrete, we perform summation of e raised to tx, and then we substitute for f of x, which is n combination x, p raised to x, 1 minus p raised to n minus x. So this is equal to summation x is 0 up to n. N combination x is a number, so we can interchange the positions. N combination x And then because we have e raised to tx and p raised to x, then we can combine p and e raised to t, and then we raise everything to x because the two are raised to x, and then we have 1 minus p raised to n minus x. Now, if we expand this third line, if we expand it, when we start from 0, then we shall be talking about n combination 0, p, e raised to t, and everything is raised to 0, and then 1 minus p raised to n minus 0, which is just n. When x takes value 1, we have n combination 1, p, e raised to t, and the whole bracket is raised to 1, and then we have 1 minus p raised to n minus 1, and this continues until we reach the last value for n. So we shall have n combination n, pe raised to t, and the bracket is raised to n because now x is taking value n, and then 1 minus p raised to n minus n. And so, okay, there is a question. So there's a question about how do we know whether to use MGF or expectation. We usually guide, if it is in the exam, we guide, we ask for the technique to be used. Like now, for the binomial distribution, it is also possible to do it using expectation. But if we were to use expectation, it takes around 3 foolscaps. So this is why I preferred to use moment generating function technique, because that one takes only 1 foolscap. So because the other one is more technical, then I decided to use moment generating function technique. And of course, we also try to make it as easy as possible for the students. So this is why I preferred to use MGF for binomial. Okay, if there is no other question, then we can continue. So we have expanded up to the 4th line, And then, as usual, we always borrow from calculus. So this quantity, a plus b raised to power 3. A plus b raised to power 3, I want to use this knowledge to continue after the 4th line. So a plus b raised to power 3, if we expand, is a cubed plus 3a squared b plus 3ab squared plus b cubed. We want to use what we know. We want to move from what we know to what we do not know. We all know that a plus b cubed gives us the quantity to the right, which can be expressed in combination form as 3 combination 0, a cubed, b raised to 0 plus 3 combination 1, a squared, b raised to 1. So I'm using this for illustration purposes. And this second line, which ends in 3 combination 3, a raised to 0, b raised to power 3, can be condensed as summation x is 0 to 3, 3 combination x, a raised to 3 minus x, b raised to x, which is none other than what we have in our 3rd line. If you look at the 3rd line, and what we have in the last line, they are the same. So why am I comparing this? Because you see, if you look at the last line, we have a raised to 3 minus x. So a, we have a plus, and then b is raised to x. So we have b. So we are going to have, in this expansion of ours, which I'm going to show in the next slide, all we need is p raised to pe raised to t, and we need 1 minus p. And then we will write it in the form of, I'm forgetting the name of this, where we have written a plus b raised to power 3. I don't know whether it is, I know what is on the right is the binomial expansion of a plus b raised to power 3. So in our next next step, all we need is pe raised to t and 1 minus p. Just as we can see that in the last step, we have a raised to 3 minus x, and we have a in the bracket and b raised to x. So let me get the next slide so that we continue with that. Okay. So someone is asking 1 minus p. 1 minus p will replace the position of, 1 minus p will replace the position of a, and that's a good question. 1 minus p will replace the position of a, and p e raised to t will replace the position of b. And this is what we have here. If I could expand it just a little. And so if I expand it, are we able to see it? Yeah. So 1 minus p is replacing the position of a, and for b, we substitute with pe raised to t, and then where we have power 3, ours goes up to power n. So this is the moment generating function. And so you can see some of the topics we've gone through are coming up, because now we know that to get the expectation of x, if we have the moment generating function, we need to take the first derivative. So we get m prime x of t. So if we differentiate that our first line, we get the second line. If we differentiate, of course, with respect to t, and then to get the expectation, we need m prime x of 0, implying that we substitute in the second line, we substitute for t with 0, we substitute for t with 0, and if we do that, then we find that for the binomial distribution, the expectation of x is given by NP. 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 Remember, P is the probability of success. And then to get the variance, remember from the moment generating function, we need to get m prime prime x of t. We already have m prime x of t in the second line. And then under variance, then m prime prime x of t gives us the long function on the right, m prime prime x of t. You know we are differentiating that using product rule. Product rule. And so once we get the long then we need to get m prime prime x of 0. Where there is t, we put a 0, and this gives us n into n minus 1 p squared plus 1, close the bracket. I know it's a long expression, so I should give you 1 minute. And then var x is just m prime prime x of 0 minus m prime x of 0, and m prime x of 0 is squared. And so when we substitute, then we find that for the binomial distribution, the variance is given by np into 1 minus p. np into 1 minus p. So I'm just giving you some time. But of course, you need to perform that differentiation and confirm. You need to perform that differentiation later. Okay, so we can proceed. Now we know that for the binomial distribution, the expectation of x is given by np, and the variance is given by np into 1 minus p. So let's look at, okay, let me just, so expectation of x is given by np, and the variance is np into 1 minus p. So this one is given by np, and var x is given by np into 1 minus p. So let's look at an example, and we see how we can handle a question which follows the binomial distribution. Each of 4 boxes, contains 3 electric bulbs, 2 are good and 1 is defective. 2 are good and 1 is defective or bad. A bulb is chosen at random from each box. A bulb is chosen at random from each box. Consider choosing a good bulb a success. Consider choosing a good bulb a success. So what are the questions? Part A. The questions are: A, obtain the PMF of X. Obtain the PMF of X. Part B, compute the probability that Roman 1, 4 good bulbs are chosen. 4 good bulbs are chosen. Part 2, Part 2, 2 good, 2 good and 2 defective bulbs are chosen. 2 good and 2 defective bulbs are chosen. So we need to compute those probabilities. First and foremost, we need to get the PMF for X. So you see, how many boxes do we have? There are 4 of them, 4 boxes. That is just one. So these are repeated Bernoulli trials. If we pick from the first box only once, the probability of getting a good bulb, the probability of success is 2/3. The probability of success is 2/3. So P is 2/3. And we have been told to consider choosing a good bulb a success. That is why the probability of success is 2/3. So our random variable X is binomial NP. Remember we had said that the binomial distribution has parameters NP. NP. These are the parameters of the binomial distribution NP. So if someone writes like this, what they're just trying to say is that the random variable X is binomially distributed or has a binomial distribution with parameters NP. So in this question, X has a binomial distribution, and what are our parameters? We are picking 4 times from 4 boxes. So the value of N is 4. We will pick up to 4 times. And what is the probability of success? 2/3. So what is our f of X? Our f of X, if we substitute in equation 1, let us say this is equation 1. So if we substitute in equation 1, then our PMF is f of X is equal to 4x, and remember that X is the number of successes. What is the probability of success? 2/3 raised to X, and 1 minus P is a third. 1 minus 2/3 is a third raised to 4 minus X. 4 minus, but must state the values for which our PMF holds. So this PMF holds only if X takes values 0. It is possible to have 0 successes. 1, 2, 3, up to 4. And of course, it is 0 otherwise. It is 0 otherwise and elsewhere. So that is the PMF. Now, going to part B, we want to find the probability that 4 good bulbs are chosen. 4 good bulbs are chosen. And we were told that we consider choosing a good bulb as a success, which gave us a probability of 2/3. And X is the number of successes. So if we want 4 good bulbs, then actually what we are looking for is F of 4. F of 4, which will just be 4 combination 4 2/3 raised to power 4 and then 1/3 raised to power 0. And this will give us a value of 16/81. Okay, so we have answered the first part of question B. And the second part is asking us for the probability that we select 2 good and 2 defective bulbs. So that one is just, it is the probability of F of 2. It will just be F of 2 because you're looking for 2 successes. If we get 2 successes, it means that we have 2 successes and 2 failures. So that is 4 combination 2, 2/3 raised to power 2, the 2 successes. And 1/3 will also be raised to power 2. And this will give us 8/27. So this is how we handle a question which involves binomial distribution. I will send an exercise on the same to your class reps after this. Okay, so maybe we can look at the last one. We look at the last distribution for today. There is a question. What about the defective? The defective is taken care of. The question was that we get 2 good ones and 2 good and 2 bad ones. Two defective ones. So you know we are picking 4 times. Oh, there's a question what is this powerful FX99 calculator? I think my calculator is a simple one. What is the work of the? I don't understand this, Wambua. What is the work of the first time in the expression? And how is it involved in the expression? I don't understand that one. Can you rephrase the question? Rephrase that, please, Wambua. As you are rephrasing, I try to answer what about the defective, and then I come back to majestic. So then I will answer Wambua's question. Okay, so someone asked, what about the two defective? And I was saying, you know, we are picking 4 times. We have 4 boxes. So we are picking 4 times. We are picking a maximum number of 4. And so, you know, I had said, when I was even explaining about the binomial PMF, when I introduced it, I said that X represents the number of successes. In our question, the number of successes is 2. The number of successes is 2, but we are picking 4 times. So if I pick 4 times and I find that only 2 of them are good, then it means that the other 2 are bad. So if I look for f of 2, it covers the situation where we have 2 good ones and 2 bad ones. So to get 2 good and 2 bad, simply look for f of 2, where 2 of them will be good and the other 2 will be bad. So, yeah, Odero has answered a question there. Let me go back and see. Yeah, so I've answered what about the defective. I hope it's clear to Mwaura. So asking how this, oh yeah, Majestic, your question has been answered by, and I think Degwa is also trying to answer it. And also Odero has said you just do n combination R, and that is what me I have on my simple calculator. And you just, in my calculator, I don't have to do shift. If you do in my calculator, if I do shift, then I'll get n permutation R. There's a difference between n permutation R and n combination R. But it is just n combination R, really. So Wambua, did you type your question again? Because I don't seem to understand it. Does it mean that probability that other 2 are defective is 1 minus 8 over 27? No. You guys are overreading. Eh? You see, when I write here f of 2, what am I really saying? I'm saying that we have picked 4 bulbs. We have picked 4 bulbs. We have picked them. We picked one from the first box. We picked another one from the second one. We picked another one from the third one. We picked another one from the fourth one. And that is why, where we have n, it is represented by 4. Now, if you want to find, if you want the probability that you get 0 good bulbs, 0 good bulbs, what are you going to do? Where I have put 2, you'll put 0. It gives you the probability of picking 0 good bulbs, because we had defined X to be the number of successes. So the probability that I pick 4 bad bulbs
is going to be given by f of 0 because I have picked no good bulb, none. So I'll just get f of 0, which is 4 combination 0. If I want the probability of picking one good one, and 3 bad ones, then I will look for f of 1. So if I put 1 where there is 2, it means that out of the 4, only 1 is good. So the probability of having 1 good one and 3 bad ones is f of 1. So the probability of having 2 good ones and 2 bad ones is f of 2. Let me look at the chart again. So Rashid, I hope it is clear. Okay, Wambua has typed, let me look at what he's saying. What is the work of the first term of the expression? 4 combination 4. What is the work of the first term of the expression? For this example, it would be 4 combination 4. That one, I think what Wambua is asking about is this part here, n combination x. That is the first term of the expression. And these combinations and permutations, there is a topic in calculus known as permutations and combinations. Permutations and combinations. And in Chiromo, we teach this one to our first years. And I think you are also taught this because you also taught calculus, permutations and combinations. Combinations. It is taught in Chiromo in basic maths, SMA 101. And these two topics, they talk about the number of ways of making selections, whether if the order matters and if the order does not matter. So this question that Wambua is asking about the use of this first part of the expression n combination x, it gives you the number of ways of picking. So for one of them, the order matters. For another one, it does not matter. So it's the number of ways of picking. Of course, 4 combination 4 is 0. And 4 combination 0, maybe, I don't know whether you are having a problem with this combination. Maybe I should just explain a little bit more. What is 4 combination 4? What do I mean by that when I say combination? I think some other lecturers use a different, I don't know. I should say this in the general form first before I come to this. So suppose we have n combination x. And I think some people say n choose x. Some people say n combination x. But if this is giving you a problem, then during your free study time, look at permutations and combinations. Okay, now let's go to the expansion of this one. When I have n combination x, and some people usually say n choose x, what do we really mean? We are saying n factorial over x factorial n minus x factorial. This is what it means. So you can either use the calculator, like that friend of ours who asked how he can do that on the calculator, but it is also good to understand the basics behind it. So for example, for combination 1, or for choose 1, as some other people say, is going to be given by 4 factorial over, is going to be given by 4 factorial over, it will be given by 4 factorial over 1 factorial and 1 factorial is multiplied by so it is 4 factorial over 1 factorial multiplied by 4 minus 1 factorial. So what is this equal to? This is the same as 4 times 3 factorial. And there's a reason why I'm writing 3 factorial. Why? Because I'm looking at the denominator. Over 1. Of course, 1 factorial is just 1. What is 4 minus 1? It is 3 factorial. So this is why I wrote 3 factorial, so that this one and that one will cancel out, and then I will get 4. And this is why I said that for combination 0 is 1, and it is also equal to 4 combination 4. For combination 0 is 1, for combination 4 is 1. Any other query? So this is what the first expression is all about, Wambua, and any other person who was wondering about it. So that is how we handle it. So even if you go to the calculator, that is what the calculator is doing. Okay, thank you, Majestic. I can see you are saying thank you. Rashid is also saying yes. So what I explained to him is clear. Daniel is asking, would you be asked to find probability of items less than n? Okay, first and foremost, the items are not n. In that example of ours, we have 4 boxes. So the boxes are the ones which are 4. In every box, there are 3 bulbs. 2 good ones and 1 bad one. So please don't confuse the boxes. You know, the boxes were 1, 2, 3. There were 4 boxes. That was the first one, second, third, fourth. And this is why, because there are 4 boxes, that is why X is ranging from 0 up to 4. Repeated Bernoulli trials. Because you may get 4 successes or 3 successes or 2 successes. Why? Because you are picking 4 times. You cannot get 5 successes because you are picking only 4 times.
Let me look at the chart again. So I've just corrected that. N is referring to 4 in that example of hours. Okay, yeah. Thank you, that's fine. Yeah. Somebody's asking a very good question here, which I think is that yeah, somebody's asking here, will the probability of getting at least 2 good bulbs and the probability of getting 2 and 2 bad bulbs differ? Yes, those probabilities will differ. And this, Dennis Kialo, I think you have understood the language of statistics, because at least is very, very important. And the question that I'll give in the exercise will involve that. So the probability of getting at least 2 good bulbs and the probability of getting 2 good and 2 bad, they are different. Yes, Dennis. And the question I'll give in the exercise will involve that. So just to give you a hint on how to do that, because Dennis has asked. So the probability of getting at least 2 good bulbs means you get 2 good bulbs or 3 good bulbs or 4 good bulbs. So it includes 2 or 3 or 4 bulbs being good. So it will be different from what we have just calculated. Any more questions? Any more questions? I think it looks like you really like the binomial distribution. What did I want to do? So I will send, next time we shall look at the final distribution. Next time we shall look at the final